first of all, I would like to thank the organizer for providing me this precious opportunity to present the preliminary results of our work, which was done in collaboration with my PhD supervisor Agata Różańska and other collaborators. And I will basically talk about the recent recent work we have done from the observations of Chandra X-ray satellite. As we know, Sagittarius and our galactic center is very interesting for observation and doing science, not only because of it is our galactic center, but also because it has a very interesting and unique environment, providing different phases of clouds with different temperatures. So it's very interesting for the study, and it has a well-established value of the mass of the central black hole of the order of a million times massive than the Sun. It's proposed within this radius of 0.015 parsec. It's proposed in that paper, and it also contains different regions with different temperatures. The one so-called cold molecular cloud regions, which is with a distance of approximately 15 arc minutes from these Sagittarius A stars, and which is studied by using the XMM Newton observations, and there was a paper about the study of these regions, which emits neutral iron K alpha line at this energy, and these iron lines are produced due to the reflection of the hard X-ray continuum from the center by the material containing iron. And it also contains hot plasma with electron temperature corresponding to 2 keV within 1 arc minute, which emits actually hot iron K alpha line at this energy 6.7 kilo electron volt. And there is a region just close to the central Sagittarius A stars, but in east side, so-called Sagittarius A East regions, which is supposed to be probably caused by the supernova remnants, and since the distances are of the order of magnitude, so these regions can be well studied and resolved by the Chandra and Suzaku satellites because of their high spatial resolution. And we can find extensive studies that have been done on this particular region in these following papers, and recent result is reported in this paper by Wang et al. 2013, which are more or less consistent with the results that we obtained. And this is the description of the observational data that we used in our calculations that I will be showing in the following slides. And we downloaded the data from this instrument of Chandra within this field of view, and these observations were carried out in 3 subsequent number of observations with these close dates. So we produced the data by co-adding all these 3 observations, and we obtained this total exposure time. We use the data of this total exposure time, which is good time interval data, co-added total exposure time of 134.77 kiloseconds, and the target coordinates were this one, right ascension and declination respectively. And we used CIAO 4.4 version of this software, and this for calibration and other stuff. So we use this tool that are available in this website of Chandra satellites. although the exposure time was bit smaller, to discover and to study the filaments that are seen in the region, but we were able to mark out those filamentary regions which were observed by Johnson et al. And then this is actually the exposure corrected flux image. During this correction, we corrected it for bad pixel removal and charge transfer inefficiency, and we made a background correction. This green ellipse shows the background regions we have chosen because it does not have any point-like sources or any flaring kind of situation. So this is the minimum level of the flux, and we made a correction accordingly. And this cross sign at the middle shows the position of the Sagittarius A star. And this image is produced by subtracting the continuum level from the iron line energy, and it is produced in this energy band where the iron line occurs. But still we have some kind of bright sources which we could not remove because of this fact that because of the emission from the cold iron line overlaps with the broad line energy band. It's reported in this paper. But still this spectra is enough able to study the iron line emissions, properties of the iron line emission. And then we again, according to the iron line region image, we separated these regions into different regions, which is the one known as Sagittarius A star, enclosed by this big circle, and we divided these circles into 9 different regions, and we extracted spectra from each individual regions. And this actually it should have also one circle here, because we divided this, we missed it actually. We divided this into 3 regions of different radii, 5 arcsecond, 10 arcsecond, and then 15 arcsecond. And then we because we did this because we want to know the spatial distribution of the iron line profile, and we want to answer this question, just to know this question, that how far from Sagittarius A star source emission, iron line emission is crucial. And these are the spectral fitting done with SgrA, which is the X-ray spectra fitting software available in this website, and we set the chi-square statistic for this spectral fitting. This red line shows the total model assumed, and which is this Bremner-Starlung model plus thermal Bremner-Starlung model for this plus for this continuum, and plus this line Gaussian line spectral fitting for this iron line. And each individual spectra are obtained from those individual regions. So these are the spectra of this region 1 of the Sagittarius A East regions, and region 2, and accordingly. So it can be I will show the table of those fitted parameters. We show that the temperature in all these regions ranges from lowest 1.9 up to higher to 3.6 keV. And these are respectively 7th, 8th, and 9th region of Sagittarius A star, enclosed by this big circle. And these regions are the are the regions that we divided into 3 circular regions of different radii, and this spectra is of the radii of 5 arcsecond, 10 arcsecond, and 15 arcsecond respectively. And this is the table, and we also did same. We also did same spectral fitting with a different model. We assumed power law fitting plus Gaussian, which is modified by a galactic absorption model, and then we compare between the different parameters. And what we noticed is that the energy edgeways iron line is present is almost same in all these models. So this energy is independent of the model assumed. But there is a difference in the equivalent width of the iron line profile, and it follows that this equivalent width of the iron line profile in thermal brainstorm is lower up to this 9th regions than in the power model assumed, and opposite in the Sagittarius A star regions. I mean the equivalent width of the iron line in power law model is greater than the thermal brainstorming model assumed. And this is we plotted it to study the distribution of the equivalent width of the iron line from the different regions, and Sagittarius, and we see that from this plot that the Sagittarius A star lines are all of the lines are strong with the value of equivalent width ranging from 1.2 to 5 keV. But in case of these regions which are very near to this Sagittarius A stars, like this first circle represents the region with 5 arcsecond, and then second with 10 arcsecond, and then third with 15 arcsecond. The value of the iron line equivalent width of the iron line profile is smaller, which is similar with the recent result reported by Wang et al. in this paper, which suggests that the presence of an outflow from the accretion flow into the supermassive black hole. And this is the velocity profile of these different regions obtained from this thermal brainstorming model assumed, which shows that these regions that are in the Sagittarius A star regions, they are flowing to the central object away from the observer with the velocity ranging from 1000 to 2000 kilometer per second, and the matter which is present in the region closer to Sagittarius A star within the region of different radii, which is outflowing with an average velocity of 500 kilometer per second outward. And this is the temperature distribution of the matter, which shows that this hot plasma around Sagittarius A star has almost constant temperature, but in the region which is quite far and so-called Sagittarius A is, the temperatures are quite different, less. And these are the conclusions that we made on the basis of the observations we got. So the conclusions is like we analyze the spectra of each region separately just to to study the distribution of the iron line profile from the different regions, because in most of the studies that have been done before, they just assume they just divide the regions into 2 or 3, and then they study. So our study is different from others, because we divide the whole region into many regions to see how this iron line region iron line profile is distributed among all the regions, and this is the same conclusions that I discussed in the previous slides. And we can suggest that in observations this iron line is relatively hot than observed in other papers, because but it is obvious that we studied more closer region to the central objects, because the same similar kind of study done by Ponti et al. In 2010, they suggested the cold iron line, but it was quite far away from the central region. Thank you for your attention.